So what we'll do now, let's try to do a simple design example. What we'll do, yeah, I can basically copy, I have it here. Yeah, let me copy this. Great. So now the circuit is slightly different. We're just going to have an RC here. So let's look at the equations. We have two poles. We don't have the RHP0. Let's assume this RC is exactly 1 by GM2. Okay. So the 0 is not there at all. But instead of the 0, we have a third pole. So let me write it. Third pole is approximately at 1 by RC times C1. And what can you say about the phase margin? How will it change? I mean, first the phase. What should change here? This is the phase added by the first pole. Second pole. This was the phase added by the 0. Now the 0 is not there. So this is not. Okay. Phase margin will just contain this. Same thing as we did before, just that the 0 is not there, so its effect is not present. Yeah, pole 3 will add, we'll assume it's at a much higher frequency, that it's very small. So we'll have some theta. So let's say what we can assume, maybe, yeah, okay. So let's say we are given a particular unity loop gain frequency. Feedback factor is also known, and you are asked to drive a particular load capacitor CL. Let's say these are the only things given to you, right? How do you think you will proceed? I mean, let's say I give you this to design, right? Let's say I know I want to drive a particular load capacitor, and feedback I wanted to have a closed loop bandwidth of roughly something, right? So I know the closed loop bandwidth, so approximately unity loop gain frequency is also that. You're not given, so what do you do? And we have to assume, right? Specification is, this is the only specification. To design this op-amp, you need to know what phase margin we are going to design for. So we can start by assuming phase margin, and what value do you think we can assume? Huh? Yeah, I mean, we can assume 76 or 60, anything, okay? Remember, 60 is to make sure the closed loop response shows no peaking. 76 is for fast settling, for critical damping. Okay. So you can assume, but typically you don't exactly assume 60, because as we know, we have this third pole here. Plus also, we also know that in this first stage, we have some extra pole due to this guy. So it will add some extra phase here and there. So you can add some plus or minus 3 degree, margin. Okay, so now phase margin is given. This is the expression for phase margin. So what will you get now? You can get P2. So I'll say from phase margin and the unity loop gain frequency, you can get where the second pole should be. Okay? Because farther your second pole is from your unity loop gain frequency, your phase margin is better. So phase margin is predominantly determined by this ratio P2 by omega U loop. So now my second pole is known. From this, can I find something? My second pole is GM2 by CL. I know the load capacitor. So from P2 and the load capacitor, I can find GM2. Okay. So now we exhausted this information on this and CL. Sorry, I just use CL for now. Yeah. So I need to still figure out GM1. Let's say load resistance is not given to you. Yeah, whatever is there. Yeah. Yeah, so I still have to find out GM1, right? Basically what I am trying to do is the following. First I am trying to design this at a block level. Okay, maybe clarify that. So first I want to decide it at a block level. So I want to find the values of GM1, GM2, CC and RC. Okay, because all these guys are parasitics, that is not so much under your control in the first place. So I have found out the value of GM2. So still I need to find GM1 and CC. What can I use? What do we know? How do you know? Yeah, the unity loop gain frequency is beta times GM1 by CC. But I know beta GM1 by CC. But I know neither GM1 nor CC. What do we do? Huh? Yeah, what did you say? That's the only way. I mean, this is the, see, it's like one equation, two unknowns, infinite possibilities. As a designer, you make some reasonable assumptions and do it. So like he's saying, one thing you can do is, why CC is CL by 10? Why CL by 10?
CC should be very small than CL.
We didn't make anything like that, right? The assumption was C1 must be smaller than CC and CL. Right? I mean, CC can be smaller than CL or greater than CL, we don't know. Right? There is no constraint on that as far as we know. We delete it. So yeah, I mean, you can assume CC, but we know CC must be greater than C1, right? Yeah, so you can assume CC to be greater than C1, but as he pointing out, we don't know C1 also. So typically from, let us say from your design experience, you will know what will be the range of C1. Otherwise, we will see how we can get an estimate of C1 now. So let us say you somehow find C1, rough value. You can choose CC to be greater than that. So let us say 5 times or 10 times greater than that. So once I know CC, I know omega U loop, I'll find GM. Okay. So this will decide at a block level, but your job is not to make this quadrilaterals. You are supposed to design those quadrilaterals using transistors. So let's see how we might do that. Huh? How do you propose doing that? That's also fine. Yeah. Like, I mean, see, I am just giving you one way, right? This is not the only way. Like he's pointing out, I mean, we typically saw GM2 is larger than GM1 because GM2 is supposed to drive the load. So you can always choose GM1 to be slightly smaller than GM2, say some 3 times, 4 times or 5 times GM1. And then you find CC from that. But you should also make sure that the CC is greater than C1 after that. Because we have assumed that P2 is GM2 by CL. That is based on the assumption that C1 is much smaller than CC. Right? Yeah, that's also completely fine. I have just taken one route. Anything that works is fine. So let's see how we can do this transistor level thing. Let me actually copy paste. Let me erase. What can I do? Yeah, I'll erase this. Reduce the size here. Visible, right? Okay. So just to remind you, what we have done is we have found GM2 and we don't know C1. So basically we have assumed CC to be greater than C1, right? Or you, yeah. And then from this you get GM1. Okay. Even if you do the other way, wherein you start by assuming GM1, you end up with CC, but without knowing C1, we don't know if that is correct or not, right? So somewhere or the other, somewhere down the line, we should get an estimate of this. So let's see. So one thing we know for sure is GM2. So which transistor here contributes to GM2? This is the second stage. The transconductor is M5. So since GM2 is known, I know GM of the transistor M5. Remember GM5 is nu COX W by L of 5 times the overdrive of 5. So I know neither W by L nor overdrive, right? So again, here again you have to make some assumptions. So there are again different ways in which you can do. one way is, if you look at the circuit here, which all transistors contribute to this parasitic capacitance C1? C1 is the parasitic capacitance at this node. Yeah, okay, definitely gate capacitance of M5. What else? Drain to bulk of M4, drain to bulk of M2. But among all these, which is dominant? Gate capacitance of M5 is dominant. So one thing I can do is, I know C1 is approximately CGS5. Okay. And I also know my C1 must be smaller than CL. Right. So I can choose it to be, let us say, CL by 5 or CL by 10, let us say. Right. And what is CGS in terms of the transistor properties? Do you remember? Huh? It's proportional to area, so again you can do it. It's basically WLCOX. Right? So COX is a process constant. So you, from this you can typically find what is my area W times L. Right? Okay. Now once again, I know I need to separately find the width and length. I know only their product. What can I do? You have to assume, and typically you can assume the length. From the process you will know. See, finally in the next week we will see, we'll not rely on these equations for designing. Okay, we will do something else in a systematic way. But as of now, the point I'm making is, if you know this information, you should be able to find W times L. Right now, equation seems to be the only way, but we will see, because in practice square law is not the exact model, so you can't completely trust this equation. And secondly, you can't exactly find what is mu, what is COX and stuff. So finally we will not rely on this equation, but I'll just go through it, assuming that we are doing through equation. In the next week we'll see how we can do it without it. Okay. But even there, the point is, if you know, let us say C1, you should be able to find what is the area. So yeah, we know the area. So to find the individual components, I'll assume the length of transistor M5. So what do you think we can assume it to be? Yeah, you can assume the minimum possible length. You don't unnecessarily want to have long lengths. So you can choose minimum length. If the minimum length, what could be an issue if you choose minimum length? Huh? Yeah, so what is the final effect on the circuit? Output resistance will be low. So that will impact your DC gain, right? So let us say you are also need to required to maintain a particular DC gain. So you choose your length based on that. Choose, let us say, some k times minimum length to meet your required DC gain. If it works with minimum length, well and good. If not, you have to increase the length. Remember, the output resistance is 1 by lambda ID, and lambda is inversely proportional to L. So the output resistance increases if you increase length. Okay. So once you know this, you can find what is W, right? So assume this, and then you will find W5. Yeah. So once you know the W and L, what can you find from this? I can find the overdrive voltage. Yeah, fine. As well as the currents in the transistor M2. Okay. I2 is the current here. Okay. Now notice that the moment you get the overdrive voltage, you should make one check. If overdrive voltage gives you this voltage, right? Once you know the overdrive voltage of M5, you will be able to find the gate voltage of M5, right? And if this voltage becomes very small, what can go wrong? Where is M4? If this voltage is small, what is the problem with M4? Drain voltage is, if the drain voltage is very small, the NMOS can go out of saturation. So you should make sure that your overdrive voltage you obtain after making this assumption is not so small, right? Because you typically know your gate is going to be at, let us say, the common mode, which is roughly VDD by 2. You know what is a reasonable voltage there, right? So you go and check. So this is one way in which you can do. Other way you can do is, see here we had assumed that C1 to be CL by 10, found the overdrive voltage and made sure it was fine. You can do the ulta also. You can start by assuming the overdrive voltage. Okay. Once I assume overdrive, we can assume the overdrive voltage based on a reasonable value here, right? Again, you know this gate is at VDD by 2. You choose something here so that the transistor is well in saturation. And then from that you find overdrive voltage. So here you know GM5 and overdrive. What can you find? I know GM5 and overdrive. What can I find from this? Yeah, so from GM5 and overdrive of 5, this will give me W by L of 5. So once again, same thing as before, I know the ratio, I need to find individually. So do the same thing, you can assume the length to be some, say 2 times, 3 times, 5 times minimum length, whatever, and that will give you the width. And once you get it, you find what is my C1, which is approximately CGS5, and this has to be greater than, smaller than CL. Yeah, as of now, looks like that's what you have to do. But in the next week, we'll see how we can design independent of this. We'll not try to extract new COX and stuff. Okay? Yeah, but as of now, that's the only way. So now you find that you have decided the width, length, current, overdrive, everything. So this guy is designed fully, right? This transistor is done. I have also used this information. So from here, I know what is C1. So which means I can make sure CC is greater than C1. I can assume CC to be some value greater than C1. So that will give me CC also. My zero cancelling resistor RC, what is its value? 1 by GM2, that is also known. Okay. So now you can find what is GM1, right? So let's continue from that. So let's do that and we'll finish today. So I know GM1 now. Let me write it. So which transistor contributes to GM1 here?
1 and 2. 1 or 2.
Yeah, 1 or 2. So basically GM1 is GM of 1 or 2. So once again, I just know the GM. I don't know the W by L or the overdrive voltage. So I don't know either of them. So what do? You have to assume one thing, and typically it's better to assume the overdrive voltage because you know reasonable voltages, right? Because remember, if I assume the overdrive voltage, this voltage is known, and that will kind of fix the drain voltage for the transistor M0, right? You don't want this drain voltage to be very low, then this guy will not be in saturation. So you have some margin. Let us say, assume that this requires some 200 millivolts or something. Based on that, you can find what is the gate to source voltage, right? Because I know this is at VDD by 2, this is at 200 millivolts. That is the assumption that we have made. So I'll say, assuming let us say VDS of M0, you can get V overdrive of 1 and 2. Okay, and once I get the overdrive of 1 and 2, I know the GM. What can I find? Sorry? Yeah, W by L ratio. So this will give me W by L of the transistors 1 and 2. Again, I have to individually find the length and width. What do? You have to assume the length. Again, depending on the gain. If you find that the gain can be met using the minimum length, well and good. If not, you keep increasing it. So this will give me the width of transistor 1 and 2. Okay. So now I know GM, overdrive and the width and length. I can also find the currents to the transistors. So this will also give me ID1 and ID2. Right? And what is I0 then? Yeah, both currents are same. So I0 is essentially 2 times ID1 and ID2. That is also. So that kind of fixes this guy. So only thing pending is this guy. So first of all, what can you say about the currents flowing in the transistor M3 and M4? Okay, they are same, but do we know the current values here?
You know the current density.
It is same as the current flowing in the transistors M1, M2. Isn't it? You have already computed it. So I know this is for M3, M4. Let us say I know ID3 and ID4 is same as ID1 and 2. That is one thing we know. Do you know anything else about this guys? Huh? Yeah, how do you know the overdrive? Yes. If you recollect, if you want to avoid that systematic offset, we told all these 3 PMOS transistors should have the same current density. So you should have the same length also. You choose my length of all these guys to be same. And then I know the current density of I by W of 3 is same as I by W of 5. From this I can get W3 and W4. So that will fix this, and I'll assume that you guys know how to make this. It's a current mirror, I am not doing. Okay. So this is again one way in which you can do. So the point I want to highlight is, at any point in real life, in design examples, you will not have, let us say, 5 equations, 5 unknowns. You'll have a sweet spot, right? You'll always have more things to find. Your constraints will be very small. It is a underdetermined system. So you have to make some reasonable assumptions here and there and proceed with the design. But always have at the back of your mind you have the assumptions that you have made, and make sure they are okay, right? Because that should not affect your calculation, because your calculations kind of did whole bunch of stuff. It assumes C1 is smaller than this, C2 is smaller than this, blah blah blah. You make sure they are all satisfied.